tried to wait as long as I could. So we're continuing with our exponential logarithmic functions. Okay, so different applications that we're bringing into perspective. Remember, kind of our branching point here is this idea that we can connect it back to like a derivative, like dA dt equals k times our original function a. Remember, the whole focus of that was that k is going to be our rate of growth or decay. Okay, so this is uninhibited growth model, meaning think about like an investment account, right? As long as you have that money invested and that interest or growth rate is consistent, it's just going to continue to grow without bound. Okay, nothing's going to stop it. So this is where that's coming from. Okay, now something else we took from that, though, remember, was this idea that one of the things that's kind of helpful to discuss is that doubling time. Okay, one of the things I pointed out is you always use the rule of 70. You do 70 divided by whatever the percent that you're growing with is. Okay, now the more appropriate way to write that for our purposes is going to be T with an uppercase, just to say, hey, this is our doubling time. Instead of using lowercase, I like the fact that the book did use that separate variable here, but it was the natural log of what value that we focus on. All over K. 2, right? And remember, I was trying to say, I know Wednesday, my brain just shut off on me in middle class, so I apologize about that. But the whole idea there is think about like doubling a multiplying by 2. That's where it comes from. Just remember, though, K is going to be the percentage that they give us to work with. So for this particular problem, they want us to use 4% and determine how long it takes to double. Now, does it really matter that they said 2006 for this problem?
No, they did not determine like a period of time.
All right, that's just telling us when we're starting, but make sure you see all they want to know is how many years it takes to double. So everyone go with that? Now be careful here. The reason we definitely want to use natural log of 2 for our course perspective is they're going to look for like answers rounded to the nearest 10. Okay. If you try to plug that into the whole rule of 70 thing, it's not going to give us exact answers. However, though, when you step out of this class, let's say you are running a business and you're working to try to get someone to invest into whatever you're working with, right? The rule of 70 is a quick way to just say, hey, look, we can use this just to kind of approximate how long it would take this investment to double, right? Or if you're dealing with loans and interest, that would be something to make sure someone understands clearly, right? That, hey, be careful with how you handle this because of such things, making decisions for your own financial stuff, right? So keep that in mind. So for this particular problem, we'll do that natural log of 2s, divided by 0.04. Now make sure K here, you see that we should be using a decimal percentage, okay? If you use the rule of 70 to compare that, use it, the percentage as you see it. Okay, that's one of the tough things that, like this little thing they put in the book may not seem obvious at first, but make sure you see here, like when they were transitioning from, well, this isn't the one I copied. From the book itself, though, it shows that you had to multiply by 100 over 100 for the rule of 70. I thought I had copied it over, sorry. Are y'all getting, though, 17.3? 17.3 what, though? Well, no, the units of measurement, sorry. It'll be years here, okay? Now, the rule of 70, is that horrible difference? Depending on how you round it, could make a pretty significant difference, right? Between 17 years and 18 years. But hopefully you see there, like the reason it's a nice little quick estimate is it's pretty close to what we want to talk about, okay? one thing I learned about, like I think I shared with y'all on Wednesday, was when I was looking to sell insurance with a local company here. They also had investment opportunities and they talked about the rule of 70. And when I did the math doing the natural log 2 divided by that, it was like, hey, it's actually a couple years less than what they're saying. It's even better than what they're showing. So now be careful here. This just says, when will the demand be double that of 2006? So once I get the year, they want to know what year that will be. Okay. That's the one thing that when I was looking at the book, please let me know if you get a question like this on the homework and it's not clear. I will do my best. To me, this would be a great like multiple choice problem for this test coming up, right? I will do my best. So like if it's a multiple choice problem, it'd be very clear, either 17.3 years or what, 2006 plus 17, wouldn't that be 2023? By the year 2023, it should double kind of thing. Everyone follow me on that? But when I looked it up in the textbook's answer key, they didn't give the answer I felt would be appropriate for this question. But I will do my best for the test that you'll, like I said, multiple choice I feel is great here. And you'll see either 2023 or 17.3. Okay. Any concerns with that though, as far as cleaning up what I messed up on Wednesday? Now, remember, this is all built around the idea that the derivative of an exponential, right, gives us that exponential back times the chain rule. So that's what we're kind of focusing on here. Um, one of the things that we're going to work through is kind of better understand how to use a derivative, and then we got to learn how to go backwards, right? What we call an antiderivative at some point. Once we get to the antiderivative, we can better explain why this connection works. But right now, we just kind of have to, that's why the book just kind of gives it to you. This is what we're using. Okay. With that said, let's go look at another problem here. Now, the one thing that just be prepared for with some of these problems is always pay attention to the information that they give you. Okay. Watch for keywords and all of that. That's definitely something that you want to be careful with. It's like, as we're going through here, this is franchises for pizza shops throughout the country. Sorry, they're selling franchises for pizza shops throughout the country. The market manager estimates that the number of franchises will increase at a rate of 10% per year. So what are some keywords from that part that helps you out? Definitely want to make sure we highlight 10%, right? But I would also, with that, highlight increase. Okay, because what other word could they throw in there? Decrease, right? So increase positive, decrease negative, but make sure you catch that. Now, this part is important as well. Okay. When you see this statement, how is it increasing? Is it increasing linearly, quadratically, some other way? What does that tell us? So when we take a derivative of a function, right? What function do we get the same thing back times something, some other value? A constant value specifically, huh? All right. I couldn't hear you. I'm sorry. What do you mean by that? Yeah. So if you had a derivative, a function, right? You take the derivative of this function, we're going to get the same function back times a constant multiple. What's the only function that when we took the derivative, we got the same thing back? Not linear. So I'm just simplifying it, right? Ignoring the initial value, of course, right now, okay? But e to the kt, well, the derivative of that is ke to the kt. All right. Now keep in mind, I ignored the initial value when I wrote that. So we would have to make sure to discuss how that plays into what's going on. But just keep in mind, like if the initial value was a part of it, that would be here. So you'd have to do 0.1 times the initial value. Okay. So whenever you see this statement here, what we want to make sure we're saying, hey, I'm dealing with an exponential growth. All right, uninhibited growth would be another uninhibited exponential growth. What they're saying is, hey, we're just going to keep growing and growing and growing and never stop. Okay. Now, as mentioned, though, that percentage they gave us means that, hey, that's what I'm going to be thinking about as far as our K value is concerned. All right. But this part here, please understand when I highlight this part, what I want us to make sure we're practicing is, hey, that means I'm dealing with an exponential function. I took a derivative of a function and it's going to have the same thing in the result. The only function that does that, exponential. Okay. Now, the 0.1, well, hey, that's a chain rule. That's going to come out through a chain rule at some point. Okay. Because of what we're working with. Now, with that said, this particular problem, we did get K equal to 0.1. Always be careful to remember to change it to a decimal. And it wants us to find the function that satisfies this equation. And it says, assume the number of franchises at the beginning is 50. So t equals 0. What this is an initial value. Okay. We're starting with 50 franchises. We want to see how we grow here. Now, as far as this is concerned, we can then kind of build our function, right? So for part A, we can say, hey, n of t equals some initial amount, right? We're going to go and deal with that, which we should already know the initial amount because they gave it to us, but we can look at that in a second from another perspective. E to the 0.1 t. And as I mentioned, the C is what they gave us from the textbook, right? They just say, hey, use C, that's going to be some constant multiple. That's where the letter C comes from. I'll better be able to explain where the C idea comes from when we get to those antiderivative situations. Once we get there, we can better understand that. But for our perspective, just know the nice thing about exponentials, if you plug in the values that we have here, the initial value that we were given, so n of 0 equals 50, well, this will equal CE to the 0. 0 times 0.1 is 0. Well, what is anything to the 0 exponent equal? Right? Anything to 0 exponent is 1. Okay. So what does that leave us with when we write this out? And we see that gives us C equals 50. So if C is equal to 50, that means this value here, as you probably might remember from college algebra, that's usually going to be your initial amount, okay, for an exponential function. Okay, so if you want to, you could have just wrote it from the beginning that like, hey, since this is my initial value, specifically t equal to 0, we could have just wrote our function out instead of going through this extra step to say, hey, this is 50 e to the 0.1 t. Okay. Which if you connect this back to like compound interest, right, that we used A equals PE to the RT, where the P represented the principal, which was the initial amount of the investment or account that you were working with. Any concerns with that? What is part B wanting us to do then?
Estimate how many franchise after 20 years.
Right, so where are we plugging in the 20 is the key. Right, we want to go plug that in for T, right? So hey, for that next part, we're going to say, hey, n of 20 equals 50 e to the 0.1 times 20. Okay. Now, where should you round your answer to, by the way? If you're talking about the number of franchises in 20 years later, how should we round our answer that we're finding? Yeah, make sure you catch that. Like, just think about it. Yeah, the fraction and decimals, those aren't insignificant, but if we're building a report to kind of talk about, let's make sure that we keep it as to say, hey, when I deal with this, we'll have 369 and that 0.45. Well, we might have some being built, but these we'll call that these are the ones that are established. Okay. Now, one thing I will point out is like as you move forward in this, one of the things that you'll find is sometimes this is based on statistics, right? Some of these models are great to help us get an idea, but that fraction means that there might be a little wiggle room. So we can then go to the stats, right, to kind of discuss like, what's the amount of error we can talk about, right? A little above or a little below. What that all depends on the statistic size that built the model. Okay. Are we all good go getting to 369? I saw most of y'all checked it out. All right. What does it want me to do for part C then? It says, in what period of time will the initial number of 50 franchises double? I think that's the most direct part. Right now, if you wanted to, you can do the fun part and say, hey, let's set it equal to 100. But remember, that's extra work you don't have to do. That would go back to where I showed you how we got to the capital T situation. Divide both sides by 50. What number do you get? 2. You have to use then the natural log to get the E to drop out, right? Well, there's where the natural log of 2 comes in. But we use a capital T here just to say, hey, this is going to be specifically for my doubling period. Okay. Sorry, I've got the right franchises at that 369 earlier, but make sure you see this is 7 years for it to double. So with 20 years, it almost doubled 3 times, right? So 50 to 100, 100 to a 200, 200 to 400. Any questions or concerns with this? Now, why didn't we go get a derivative here, right? Well, make sure you see they gave us a derivative to kind of set what type of function we're working with. This derivative statement, right, is what told us, hey, we're working with exponential growth. So that's one of the perspectives that we want to be comfortable with here. Is like, hey, when they give me this function that's given as a derivative, recognizing exponential growth. So it's one perspective, okay? As you move forward, make sure that you understand that the way they ask questions determines on how we needed it, right? They might go and say, hey, what's the marginal increase of the number of franchises after 20 years? Okay, or in the year 20. That would be where we want to then use the derivative and plug the 20 into that, the marginal increase for that, okay? So for example, here, just make sure you see they already gave us the derivative, so that's kind of nice. It's 0.1 times the 50 e to the 0.1 t. Don't go differentiate if you don't have to. Everyone follow me on that? So that would be what, 5 e to the 0.1 t? That would represent our derivative function, okay? Well, just out of curiosity, let's plug 20 in there just to see what happens.
Or the T, right?
For the t, right? But keep in mind, I'm just doing this as a talking point, okay? So I'm going to find this, and what I got is about 37. Now, remember, the reason I use marginal, that means in year 20, how many more franchises can we expect to appear the next year? 37 more. That's what the word marginal growth comes in. That says, hey, when I look at the derivative of year 20, that gives me an instantaneous rate of change, right? It's a linearization, right? We're looking at a tangent line, so it doesn't perfectly match the graph, but it gives me a pretty accurate estimate to say I should expect 37 more next year. right? So year 21, 37. What's 369 plus 37? So we just kind of look at it, since we already calculated, that's why I chose that one. 406? Does that agree with the 7-year estimate for doubling time that we just used? It's pretty close, right? Because remember, if we go 7 years, 21 years would be 3 doublings, right? So 50 to 100 is your first doubling, 100 to 200 your second doubling, 2 to 4 would be your third doubling. So hey, 406, that's pretty close, right? And remember, again, that's just an estimation. We could have just plugged 21 into our function to get a little bit closer estimation. Any questions or concerns so I can help with how we got to the original model and used it moving forward? Or feeling okay with that doubling time stuff too then? All right, so with that said, then, if you're comfortable with that, let's jump into a different type of model because it's not everything's going to have this uninhibited growth. Okay. This new type of model, what a key word you want to hear would be like logistic growth, right? What happens when we're looking at something that grows but is limited based on something that's keeping it from growing beyond what a certain level is concerned. I don't think I picked it, but like one of the problems that I did like was talking about fish in a pond. Okay, if I dig a pond in my backyard and I put, say, 20 fish in there, okay, what would determine if they can grow, right? So what are some things that if you dig a pond and you put fish into it that affect the growth of that fish, of the fish in the pond, sorry,
Eating them.
the food that's available, right? The weather would probably affect that, right? These would be things we need to consider, right, as we build a model. The size of the pond would be another one, right? All these things affect that. And if we just take the size of the pond, you can't have, this massive amount of fish because it's a pond, right? They only have so much room anyways. So all those things give us something that says, hey, there should actually be kind of a cap that limits how much we can grow here. Okay. This is where these logistic models are going to come in and help us out. Okay. Now you'll see here with this one, it says that suppose that Spryborg Incorporated induces a new computer game in Houston using television advertisements. Surveys show that P% of the target audience buy the game after X ads are broadcasted, satisfying the given function. Okay. So this is them saying like, how many times do we need to make sure our advertisement gets out to get the most people to buy it? Now be careful here. What values is this function outputting? So what type of number are we getting back from this? Here's our function name, right? It says P%, right? So understand that as we get something back, if it spits out a number like, say, we plug in P of 5, that's one of the ones we do have to run, okay? Let's actually go do that. We'll go back to part A. Part A wants us to plug in 0, right? But let's look at P of 5 first. Now be careful with your calculators and your parentheses when you put this one in. I would definitely make sure you're practicing what works best for you. Make sure I wrote down the right function.
Put your parentheses.
My calculator didn't need parentheses, so that helps. But the way I would use that, because you have the TI 30, right? So for the TI 30, what I would do is put 100, the division symbol, and then a parenthesis. Okay. And then you're going to put 1 plus 49, and then your exponential button. I think it should have E, and then it puts this there for you. Okay. So remember, this is for the fraction. This will be for your exponent. So here you would put 0.1, and what I would do is times 0.5. Why am I putting 0.5? Okay, this would be an issue. Remember, we've got to go plug in multiple numbers, right? And look at the numbers we got to plug in. So if you plug in 0.5, it should treat it as just 5. Okay. Now, when I close this one here, that's going to be for exponential. Then I close this one, that's going to be for the fraction. But make this would be one area if you're for those like Alexa, correct? For the TI-30, use those arrow buttons. Once you get your answer for the first one, use the arrow to click back up and then go over and edit in. Yeah, that way you save your time. I've had this trusty Casio since I was in college, and I could actually just put the function. That's the nice thing about it. Um, you could put the function in there too using your answer key, but I would have to talk to Mr. Simon about how to do that again because I'm not completely 100% comfortable with remembering how he showed me.
Yeah.
Are y'all getting that value though?
I'll put something.
Oh my goodness, y'all. I know. Ignore what I put here. I put 49 to that power. I totally forgot my E. I'm sorry. It is definitely wrong. That looks better. Is that more along the lines? Sorry about that. I put 49 to that exponent. I totally skipped E on my side. Sorry, that's my fault. Now, remember though, what I was trying to show here, the way that we would interpret this. Okay, let's just go to the nearest hundredth place, right? Second decimal, that's 3.76%. Okay. They don't really give a place to round this answer to. But that's saying that, hey, what's the number, the percentage of the target audience that buys the game? So if you do 5 advertisements, their target audience only 3%, almost 4% buy the game. Okay. So as you sit there and you scroll through Facebook, TikTok, and you get bombarded with these ads, what they're saying is, hey, if we can get you to see 5 ads, then we know 3% of you buy it. Okay. Now, with that said, hopefully what you'll see here is just first being comfortable plugging into this model because it's not necessarily a model you've seen before. We've worked with exponentials, right? But this model is different. Okay. So if I go down here, they wanted us to find the initial value. So what happens if we show 0 ads, right? How many people would buy this? Okay. Okay. So when I'm looking at, it's probably going to be 2. Just remember that that is a direct percentage. And hey, if I don't run any ads, 2% of the people that we're targeting are going to buy this game. Okay. Y'all remember Crazy Birds? Angry Birds, sorry. I feel like this would be what they did. Let's throw 1,000 advertisements out there until you get so tired of advertisements, you buy the game, so we stop sending them. I had movies about it, right? So we already found P of 5. Let's go find the rest, though. I'm gonna build a little table here for us. What? Are you comfortable with your calculator? Say, are you good with the calculator?
Oh,
No, I'm asking, are you gonna be comfortable with this? That's my main concern right now.
I am.
Okay. Are we feeling comfortable getting to the values that I have over there? Just end up rounding them to the first decimal place, make it a little bit better. That's all I did differently. Now, one of the things that you're going to see here, though, that I like about this, we're building towards a graph, right? Just kind of give us an idea. What do these even look like? Okay. Maybe you've seen them before more. Maybe you haven't, right? So let's make sure we're comfortable with what those look like. We've gathered some points to help us with it, right? What do you notice about the change in the values as we go from one to the other? It's increasing, right? So when we take the derivative, we should expect that it's an increasing function, right? For its domain. Okay. Now, the other thing we can look at here is the rate of change the same if we just look at them in pairs? Or does it change? How much does it change here, right? If we wanted to, we could skip over this and just look at pairs of 10, right? From 0 to 10, from 20 to 30. Hopefully you see there, the rate of change is not consistent between them. Here it goes from 2 to 7.0, right? So it's about a 5% change. Where here it's nearly a 30% change. Okay, so when we look at our graph, it's going to start slow, it's going to increase. But what number is going to kind of limit this growth when we talk about percentages? 100%, right? Now, with that said, do you think they'd ever really get to 100% of people buying the game? No, right? So that's going to be where the model kind of shows us that there's going to be a cap, right? Well, what number do you see in the numerator here that kind of helps confirm that? The 100, right? That's going to help you kind of have a quick example. What's going to be the cap of what I'm working with? Okay, and we're going to look at that from the graph, and we're going to look at some limit stuff as well before we finish up. Now, as far as the derivative, let's get to a new slide so we have some room here. Everyone was good here, though, as far as just kind of looking at the derivative real quick before we go find it. All right, so dealing with the derivative here, how would someone like to approach that? It's only one variable, right? But how you'd approach it and just kind of what you're comfortable with. How many of you would say, I just jump into the quotient? How many of you would use negative exponents in the product? That's where I'm leaning. Another one that I pointed out is, remember, we could also do this. All right. If you remember, this was one where when we do the natural log of that, we can switch this to the natural log of 100 minus the natural log of this entire thing. Now, you can't do any more from this because that plus sign in there. But that's another example of a way you can handle it, right? But let's go with the negative exponent, since that was the only hand I saw raised, and that's the way that I personally would approach it. Okay. But this is an example using logarithms. You just have to remember that over here, this would be 1 over y times y prime, or the dy dx we're trying to find. Okay. Over here, this would be 0 minus 1 over this. But guess what you're going to need at some point? The chain rule, right? So make sure you see that here, okay? And we'll be able to see that these should look similar when we're done. So I'm going to zoom this out over here, okay? But this is one of the ways that to me it stands out like, hey, I have a fraction here. This one's nice because that's just a constant value. Derivative of that, 0. The part that got a little bit tedious, remember, was dealing with this piece here because we can't leave that over there. Okay, so at some point we'd have to find a way to incorporate that back over here. Okay. I think a more direct approach, as mentioned, would be to say, hey, I can rewrite this function as 100 parentheses of this thing, the whole thing to a -1. Okay, make sure you see here that you can't mix those exponents. The reason I like that one too, though, is when I go to do my derivative, I can do a power rule and just say, hey, this will be -100, bringing the -1 down. But what do we need to change a -1 to? And we have to subtract 1 from it, right? So don't forget your power rule to subtract 1 there. Well, guess what? We still have to use the chain rule. Now, as far as this chain rule is concerned, the derivative of 1 is 0. Okay, so we're gonna have 49 e to the -0.13x times the chain rule again. -0.13. Now, a way to clean this one up. We can multiply the 100, the 49, and the 0.13. All of those are not with negative exponents is the key that so we can multiply these values together. That'll give us what, 637. Checking my signs, of course. Sorry, let me make sure I highlight that. We had a negative here and a negative here, so it's going to be positive. So 637 e to that -0.13x all over that other statement here, but just make sure you see it's squared. So let's just use negative exponents to squeeze in. Of course, again, you can use any of the other ways. If you want to just do the quotient rule, do the quotient rule. If you like doing the logarithmic perspective, that's a great way as well. All of them are going to have the different tedious aspects of it. The nice thing about having the 100 there, if you do the quotient rule, that first one's low D high is 0. So you just do 0 minus. Okay. Now with that here, if we want to better understand what's going on with this function, we could just start plugging values in to get to what we need to. Okay. That's not a function though that I would say we need to be ready to know exactly how it looks. We would have to deal with kind of building that graph. Are any of y'all concerned with getting to that derivative though? One thing I would point out then before we move forward, just watch out that when you're dealing with it, this piece here is the power rule. But I multiplied here because of the chain rule one time. Then I had to multiply here again to get the chain rule a second time, right? So we have to be careful because it gets kind of messy, especially now that we're dealing with those exponential perspectives. Logarithms can have that same kind of effect as well. All right. Everyone got this though? Now, if I ask you about in behavior, so the limit as x goes to -infinity of p of x, and the limit as x goes to +infinity of p of x, we could use the function itself, right? But what's the smallest percentage that we can work with here? What do you think the number would be for if we wanted to use negative? And we know we can't do negative numbers, right? But if we look at the graph from an algebra perspective, what's the smallest number we can get back? We'll approach it, but not actually get there. 0, right? Make sure you understand that hey, this is still dealing with kind of like exponential stuff, right? So that horizontal asymptote will still exist, right? If you plug in negative infinity here, though, make sure you see those negatives will work against each other, right? So negative times a negative makes it positive, meaning this whole denominator will go to infinity. With that denominator going to infinity, we have some number over that, which confirms, hey, we definitely have a 0 here, okay? Now, with that said, though, what number did we say is going to be the upper bound? 100, right? So when we look at this here, we should also be saying that, hey, when I go look at this graph, I expect the whole graph to be between 0 and 100. The range of this function would be written as such. This is what we're expecting. And remember, I'm using parentheses because we had to use the limit to describe that. We can't actually get there. Okay, nothing I plug in will give me 0. Nothing I plug in will actually give me 100. Okay. Now, the domain for this, because it's exponential, is all real numbers. So because we're dealing with something that has an exponential element, the domain is still all real numbers. Just for the sake of space, I'm going to use the double R. But let's look at this graph. Okay. What stands out to you when you look at the graph here? Does it look like it grows without bound? Or do you think there's some limits in place? What's going on at 100? What is the graph doing?
Just keep going.
But do you see how it almost looks like it's constant?
Yeah.
Yeah, I understand. That's the best we could look. If we get out to 100, we may not even notice the change going on because it's so small, right? That's why we like limits. Hey, it's just going to keep going. It looks like it just stays at 100. Now, from a math perspective, what we need to understand, it never gets to 100, but we have ways to describe it's going to pretty much approach 100. Okay. Over here, it's at the x-axis. So what number does that confirm over here?
Negative.
And well, yeah, as we go to negative infinity, though, what numbers it stay at and keeps going?
100.
Not 100.
Oh, 0.
Yeah, this one's the x-axis, right? So it'd be 0.
Can't go below 0.
Yeah. What shape would you kind of use to help kind of picture this real fast? Kind of like almost a little slight S shape, right? Hey, it starts off slow, picks up speed, then it slows back down, right? So there might be kind of a spot here that we can begin to ask, like, okay, how many ads is too many ads, right? How many ads is it going to get to a point where it's not going to make a difference on how many more people buy? Okay, it's kind of like what we were just talking about with the franchises, right? Not yesterday, sorry, not on Wednesday, we were talking about that, right? And at some point, it's not going to be worth the expected change for us to continue to invest in whatever we're working on. Okay, so for this game here, the number of ads that they show, right? You'll see here probably around 75. It's probably about 99%, I'm wondering. Right. So if we go back to our table, I think we stopped at 50, didn't we? 50, when you do 50 ads, it was already at 93%. And I went and cleared this out. It's okay, keep it. Now, hopefully you saw as far as like the limit stuff is concerned, just be careful of the fact that you had a negative in the exponent. Pay attention to a fraction, right? If the denominator goes to infinity, and that piece goes to 0. Yeah, so if I at 75, if we were to look at this here, about 75 here, the point that we're focused on would be 75 ads, and the percentage is 99.7%. Now, of course, you probably want to go closer to that 50 mark, right? Where in here would we have, almost everybody? Okay. Now, where is it increasing the fastest though? What part of this curve would you say the derivative is the greatest? Towards the front, towards the back, or in the middle?
The middle.
I would say the middle as well, right? That is, we were able to zoom in here. It's not letting me zoom like it's supposed to. There we go. Probably somewhere in here.
Like 20 and 60.
For some reason, let me click on that point specifically. That's pretty cool. But I would wonder if 29.94 is that kind of key value for the maximum value of this. Now, what you'll find is we'll have a great way to deal with this from the derivative test that we're going to go into as we move forward in the course. The first derivative, right? Remember, we talked about horizontal tangent lines. This graph doesn't have a horizontal tangent line. Okay. What you'll find is the second derivative is also helpful as well. And I'm pretty sure what we're seeing here is what we're going to end up calling an inflection point. That's why it allowed me to click on it. And I had no clue I could click on points on this graph. So I just learned something new, y'all. But what you'll see here is that might be something that comes from the second derivative of this function. Getting to that may not be fun, but it's something that comes from derivatives, okay? Any questions or concerns that I can help someone feel better about for this particular problem as we finish up today? I went and messed all this up though. We okay with those different model perspectives? Now, hopefully what you saw here for this graph, I would make sure you go look it up and then sketch by hand. Now, as you can see here, if you know your upper and lower bounds, just go over here and say, hey, here's 100. This is just us doing a quick sketch, of course. I'm going to put a horizontal asymptote, a horizontal asymptote. My graph's going to look something like this. Okay. We know this point because that's something we went and found. So make sure you show that, like, I know my initial value and where it goes from here. Remember when we did that one, we got 0,2. Right. It should be probably a little bit lower than how I drew it. But as far as like when it says to sketch a graph, this graph of the function on my test, if I want you to sketch a graph of this, that's what I would expect to see by hand. Show me where your initial value is. Show me the upper and lower bounds. Draw it out. Everyone comfortable with that? What's our lower bound probably going to typically be if we have a logistic growth model?
0.
Probably 0, right? Where did you get the upper bound from? When you looked at this function here, where do we get the upper bound of the model?
Oh, the 100.
The numerator though, right? Now keep in mind, it has to follow that model pattern, of course, okay? Any questions, concerns though? We're past time. I'm sorry. I'm not even paying attention. I'm having too much fun apparently. All right. Well, y'all have a good weekend and I'll see you on Monday.